Hi everybody, this is Dr. Bricker here with a video for Chapter 17, and I want to start with thin films and do the remaining part of Chapter 17. I just wanted to give you my take on this whole idea of thin films. So what you see here is this could be air, for example. This is some kind of film, and then we've got another material here. So light comes in, and some of the light is reflected from the surface, from the first surface. More of the light actually is refracted and goes into the film, but some of it is then reflected from this surface. And your eye is up here. So if these this first one and the second ray, if they are in phase when they hit your eye, you actually see this light. So this is called constructive interference. Now, they would both be arriving at your eye as maximums, if you think about it as a wave. Now, if they arrive and one is a maximum and one is a minimum, like something like one is a maximum, one is a minimum, these kill each other off, and you don't see anything. That's called destructive interference. So we've got to figure out, if they're arriving in phase or completely out of phase, and the thickness of the film here is called T. Now what further complicates it is when the first ray comes in, part of it reflects, depending on the index of refraction of the material, so this is the film here, depending on the index of refraction of the film, this incoming ray could actually undergo a phase shift. So what do I mean by that? So you got to think back to physics 220. So if you have a thin rope here attached to a thicker rope, and you send a pulse this way down the thin rope, when it reflects at this interface, so that's what I'm trying to illustrate here, you send a pulse, like you flick the rope, pulse goes this way, hits this would actually flip upside down and come back this way. Now that happens in film if, let me just call this like incident, index of refraction. So this will actually flip upside down if the index of refraction of the film is bigger than the where the ray is beginning. It's the same exact analogy as we have here. On the other hand, if you had a thicker rope attached to a thinner rope and you sent a pulse this way, part of it would reflect at the interface. You can see it a little bit better. So this is a whole nother situation. Thicker rope tied to a thinner rope, you send a pulse this way. Now the reflected pulse doesn't flip upside down. It just heads back this way. Now that happens with films if the incident index of refraction is greater than that of the film. That's usually not the case. Usually this is air up here, and this is the film, and then this is whatever the film is on. Like this could be, for example, air, oil, and water, something like that. Now the same thing happens at this other interface. It could either flip upside down or not flip upside down. So we have to take those into account. So if this ray comes in, the reflected ray flips upside down, and this reflected ray does not flip upside down, they could arrive at your eye one maximum and one minimum. So we've got to take that into account. So I've actually done that. I've made a little chart taking these things into account. So it's the same idea. We need the path length difference to be equal to a multiple of the wavelength to get constructive interference. Now how big is the path length? Well, it's T and then another T, because you have to go this way and then going back that way. And now in my picture it doesn't look like this path difference is T, but if the film is really thin, this size is practically the same thing as this size. I just have a kind of an exaggerated picture here. So we need the difference in path length, which is 2T, to be a multiple of the wavelength for us to get constructive interference. But we also have to take into account if the one flips upside down or not. Okay, so that's the idea behind thin films. So I've made this chart from a long time ago, and I'll give you a better picture of it. Turn the brightness down. Actually, this isn't too bad. So this is from when I was a TA in West Lafayette, actually. We want to determine if we have constructive or destructive interference. So if the index of refraction of the film is the middle value, remember there's three different values. There's the incident ray, there's the film, and then there's the refracted ray, something like this. So 1, 2, 3. Those are the three values I'm talking about. So if it's the middle value, so greater than one of them but less than the other one, that's what I mean by middle value. Literally, it's in the middle. That's not what I mean by middle value. I mean, is it greater than one of them but less than the other one of them? It doesn't have to be greater than this one and less than that one. It could be the other way around. This could be 1.33. This could be 1. This would still be the middle value then. Okay? So if it's the middle value, I've made this table. For constructive interference, we have 2t is equal to m times the wavelength in the film. That's if you see it, constructive interference. For destructive interference, this would be 2t is equal to m plus 1/2 wavelength in the film. So this path difference is half of a wavelength, and that will give us destructive interference. Now, if it's the largest or smallest, to get constructive interference, it's the opposite. 2t is equal to m plus 1/2 times the wavelength in the film. And then destructive interference, 2t equal to m times the wavelength in the film. Many times the problems will say the minimum thickness. So minimum thickness in this case means m is equal to 1 or m is equal to 0 here, and that will give us the smallest value of t. Okay? So let's just see if it makes any sense. I'm going back to this picture. So middle value, here's an example of it being a middle value. This ray comes in, it goes from lower to higher. We have a phase shift. It turns upside down. Now let's look at this interface between the oil and the water. Okay, this of oil is smaller than that of water, so it flips upside down again. So this ray has undergone 180 phase shift. This one has undergone a 180 phase shift. So those effects are in sync. So 2t times 2 times t has to be equal to a multiple of the wavelength in the film then for that to happen. Okay, so that's why this table actually works. This takes into account all those phase shifts. Now the book does a pretty good job, but there's a lot of words there, and you have to dig through all the information and sort of put it all together for yourself. So that's what this table is doing. One other thing to remind you of is the wavelength in the film is the wavelength outside of the film, just in a vacuum or in air for all of our purposes, divided by the index of refraction of the film. So many times the problems will tell you the wavelength, when it's coming in air, you have to figure out the wavelength in the film. That's all what these are, wavelength in film, etc. And then T is the actual thickness of the film. Okay, so let's look at the actual notes from chapter 17. Okay, so this is slide 59, and I've added a little bit more text here from if you printed this out earlier. The possible phase change leads to two situations. Either neither or both waves has a phase change. That's if it's the middle value. So the path length difference then is just equal to 2t. So m times the wavelength in the film is equal to 2t. And this is the part I added. This occurs if the index of refraction of the film is the middle value. And if there's only one phase change due to reflection, it's the other situation. The path length difference down here, delta d effective, is equal to 2t plus 1/2 the wavelength in the film. Okay, and that's all spelled out in the chart I made. So this occurs when it's the largest or smallest, when the index of refraction of the film is the largest or smallest. So definitely keep that little table with you. Okay, and here's kind of a synopsis. I think mine's better, but the conditions for constructive and destructive interference. This is for constructive interference, and this is for destructive. And now it says here if there are 0 or 2 reflective phase changes. So when does that happen? My table takes that into account. It's when there is when it's the middle value. Okay, and this is the condition for destructive interference, and this again, just like the table said, this is for destructive interference if it's the middle value. Okay, so this is perfectly good. I just organized it a little bit differently. So that's I already gave you my take on the situation. Okay, and that's a picture of what's going on. Incoming ray B is reflected at the first surface. Part of it's refracted, most of it is actually, and then we have a reflection happening here. This ray B and C heads towards your eye, so your eye would be up here where the pointer is, and then we've determined whether they're in phase, out of phase shift, that sort of thing. Okay, so here's an anti-reflective coating. So anti-reflective means you do not want it to be reflected. You want it to be destructive interference. Okay, so you've got to get that from the problem. So to keep unwanted light from reflecting from the surface of eyeglasses or other lenses, a thin film of material with index of refraction of 1.38 is coated on plastic. Okay, so we've got air, then we've got this coating, and then it's on plastic, and index of refraction of plastic is 1.55. It is desired to have destructive interference for 550 nanometers because that is the center of the visible spectrum. What is the thinnest film that will do this? Okay, good. So this is the index of refraction of the film right here. Okay, and we're going from air, here's the film, here's what the film is on. So it's actually the middle value, and we want destructive interference. This is the wavelength of light when it's not in the film, so we'll have to figure out the wavelength of light in the film. And really what they're asking for then is, what is T? The thinnest film. You could have the thinnest, or you could have twice as big as that, 3 times as big as that. I mean, practically speaking, you wouldn't want to do that if you were designing this anti-reflective coating. Then you don't want a really thick coating, you want the thinnest possible coating. Okay, so this is a synopsis of what I've basically said. Okay, so you go through the chart and you see that for the middle value, this is the formula for destructive interference. Now my tables is slightly different. I in my table have wavelength in the film just listed. Here they're just giving you the wavelength out of the film and then dividing it by the index of refraction of the film. So they're kind of doing two things at once. Okay, so then for the thinnest film, when is T going to be the smallest, in other words? That's when M is equal to 0. And you can put everything together, solve. 100 nanometers thickness film will kill off any 550 nanometer light that is going towards your eye. Okay, good. So interference occurs when the path length difference are the order of the wavelength, so our answer seems reasonable, 100 nanometers. Coat it with 100 nanometers and you have that anti-reflective coating there. Okay, so a film does not need to be a solid material. It could also be air. So you can put air between different materials and get all different kinds of pictures. I mean, I said usually it's, your eye is in air, but it doesn't have to be like that. You could have any kind of layer that you want to. So a thin layer of air between 2 microscopic slides pressed together can create light and dark fringes, as you see down in this picture. So we have thin film interference going on, constructively and destructively. Okay, so if you ever have oil on your driveway, if you look at it, the wind's blowing, it looks like it changes color. It's because you have this thin film interference going on. The wind is, making it thinner and thicker in different areas as the oil moves around. Okay, same thing with bubbles. So let's see, for a 470 nanometer thick soap bubble, light near the ends of the spectrum undergoes destructive interference, while light in the middle, because it's got a different wavelength, remember, undergoes constructive interference. And you can see these different colors here. If you've ever seen I'm sure you've seen a picture of a peacock, but seen it in person, what you're really seeing is this thin film idea. The outer coating of the bird is you're seeing different colors because of thin film interference. Okay, so if you see green, that means green is being strongly constructively interfered, and the absence of colors means you must have some destructive interference going on. So we've talked about double slits. We talked about diffraction gratings, which is just really a blown up version of a double slit. And we talked about thin films. We also have single slit diffraction. So single slit diffraction is diffraction through a tall, narrow slit of width A. So as I said in class the other day, make sure that you're making a little table of these formulas because you don't really have any intuition at all with this sort of stuff. You can't just think of this off the top of your head. So you need a little bit of help. The picture is slightly different. There's a big central maximum with the single slit, and then you get equally spaced patterns going from the right to the left. Okay, we have some similarities, but it's not exactly the same. So the light pattern on the viewing screen has this big central maximum. That's what this is here. And then a secondary maximum and dark fringes. We will still call the distance to the screen big L. It's just that the size of this slit here is called A. So if you take light and you shine it through a small slit like this, you'll bring out the wave behavior of light. Okay, and you can see too as you go away from the central maximum, this gets less and less bright. If you shine light through just a big hole, you would just get a spot. You shine light through a small opening, the wave nature of light is brought out. So every point on the wave front, you can think of it paired with another point that is a distance of A over 2 away. And then if we want to look for destructive interference, that would be the dark spots, the path length difference. Remember, that's the difference in path length. Has to be half of a wavelength. So when that happens, you get the dark spots. They arrive, one being a maximum, one being a minimum. They kill each other off. That's a dark spot. From a little bit of trig in this triangle right here, you can see the path length difference. That's what this is, delta R12. The sine of theta here would have to be delta R12 divided by the distance between them, the hypotenuse of the triangle. This is just to derive the formula, okay, and then we can use the results of it. We're doing it in a similar way that we did before. So this is one wave, but we're thinking about it as made up of a whole bunch of other waves. So it's a little harder to think about, I think, because it really is just one slit. It's not two. With two slits, it was easier. The light went through one, spread out, went through the other, spread out, they interfered. That was easier to visualize. This is kind of light going through one hole only, but thinking about it as a whole bunch of sort of points on that wave coming in. Okay, so this is again the condition for destructive interference, and we get this formula then. So the general condition for destructive interference, this is giving us the dark spots, A, and instead of using M, they're using P here. So put it all together, what we did on the last slide. A sine of theta P is equal to P times the wavelength. Now it still works out, just like we did before, that the tangent of theta P would be the distance to whatever bright or dark spot we had divided by the distance to the screen. So you could still use some geometry with this. This is the physics part of it, this. But then don't forget, you know the distance to the screen, you can figure out the distance to the dark spot, so you could use a little bit of trig there as well. Using a small angle approximation, sine of theta is approximately equal to just theta. As long as you do it in radians, you get this relationship. Okay. Now this P, again, it's the same thing that we did with double slit. We just called it M before. They're just calling it P to distinguish it from M. Okay, and then P is equal to 0 is excluded because P is equal to 0 is the central maximum. The equation for all the other P's locate the minimum. That's another difference between the single slit and the double slit. The single slit, we just have the formula for where the dark spots are located. Let me go back to the picture. So make sure you have a picture like something like this, maybe even a side view. Okay, and then that will give you the distance, or sorry, the angle to, you know, this is P is equal to 1, this one is P is equal to 2, P is equal to 3, and then the similar idea on the other side. Here, here, here. Okay, good. So the central maximum is twice as big. It's you know, two of these. Excellent. So here's a nice side view of it, really. Distance to the screen is still big L, just like we had before. This is a dark spot over here. Here's the next one. Goes up and goes down. Okay, good. So again, you could use some trig. The tangent of theta 1 would be this distance. You can call it y1 divided by L, the distance to the screen. Okay, good. So they tell you it's a single slit question. That's the information that you have to work with. The trig part of it, and also this part of it here. Okay, here's where the dark fringes are located then. Put both of those equations together, small angle approximation, you get this for where the dark spots are located. Again, with the double slit, you can get the bright spots are the dark spots. Here, it's the formula is just for where the dark fringes are located. Okay, so the central maximum is twice y1. So if you multiply the previous formula by 2, you get this. So the width of the central maximum. Okay, very good. So counterintuitively, it says here, the smaller the opening a wave squeezes through, the smaller A is here. In other words, the bigger this width will be. Okay, the more it's spreading out. When the smaller the slit, the more it spreads out. The bigger the slit, if it's really big, you just get one spot, right? You don't even get this single slit diffraction pattern. Here's an example. Light from a helium neon laser, okay, 633 nanometers, passes through a narrow slit and is seen on a screen 2 meters away. Okay, so be careful of the units. Typically, the wavelength is given in nanometers, so times 10 to the minus 9th meters. This is big L. The first minimum in the diffraction pattern is 1.2 centimeters. So these are always different units, like centimeters, meters, nanometers. Just be careful. So put this into meters, 0.012 meters from the central, from the middle of the central maximum. Okay, so how wide is the slit? In other words, what is A? Okay, so the first minimum in the diffraction pattern does correspond to P is equal to 1. They're telling you Y1 from information above. Okay, so think of what the picture looks like. I'm going to go back to the picture just so you remember. There we go. So that's what they told you, this distance here. Okay. So we want to figure out what A is. We just have to put everything together. You just have to sift through all the information. What are they even telling you? It'd be easy if they just said, YP is this, but they don't. They describe the picture, and then you have to get that information from the picture, and then note the units. This means nanometers. This was given in meters, distance to the screen. This is Y1, which was given in centimeters. You put it into meters. Be careful with the units, and you see that it ends up being in meters. So 1.1 to the minus 4th meters would be 0.11 times 10 to the minus 3rd, or in other words, millimeters. Okay, so this value is typical of slit widths. The A really is for aperture size. That's what the A stands for, but slit width here. Okay, and then you can take a look at the video concerning homework 8 to see 1730. Okay, so this stuff is, like I was saying, there's not a whole bunch of intuition with it, but it's really, really cool stuff. When you do the diffraction grading lab, you'll see that this actually works. You shine light through a small opening and the wave behavior just appears. So it's really sort of magical to me in that respect. So make a nice little section on your formula sheet. Definitely have a double slit section, diffraction grading section, thin film section, probably a picture for all of those, and then the single slit too, picture and the equations that go together with that. Okay, so really get organized with chapter 17. You really have to rely on that when you're dealing with things that you don't really have a lot of intuition with. And then on the other hand, if it's a double slit problem, you have your double slit section. That's the only thing you can use, and there's just a couple of equations there. Okay, I will talk to you soon. Hope you're enjoying the nicer weather.